Come on, my dears, let us proceed further in chapter number 7. Let us see some 2 extra questions not given directly in the textbook, just for your kind knowledge and reference. Look here. Let us see some points of differences between electron and hole. Okay? Let us see some points of differences. Here I am writing for electron. Here I am writing for hole. What is electron? You know its introduction. It is a realistic particle. It is a realistic particle. And hole is simply our imagination. It is not a particle. It is not a realistic particle. That's what I written here. It is a real particle. It behaves like a real particle. It behaves like a real particle. Actually, it is not a particle. Hole is not a real particle, correct? Fine. Then electron behaves like electron has a negative charge. Electron has a negative charge. It is a realistic particle. It has a negative charge. And here hole, you know, it behaves as if it has a positive charge. Actually, it does not have any charge. But hole behaves as if it has positive charge. Okay. Third, it is majority charge carrier for N-type semiconductor. You know, free electrons are majority charge carriers for N-type semiconductor. And what about holes? Holes are majority charge carriers for P-type semiconductor, isn't it? Fine. Number 4, it is minority charge carrier for P-type semiconductor. Free electrons are minority charge carriers for P-type semiconductor, and here holes are minority charge carriers for N-type semiconductor. Okay. So these are the 4 points of differences between electron and hole. Please prepare them. Okay. Then we go for some points of differences between N-type semiconductor and P-type semiconductor. Let us see one by one. First, to prepare N-type semiconductor out of tetravalent semiconductor, we need to add pentavalent impurities. See, last time we had studied to prepare N-type semiconductor from tetravalent semiconductor, we had added pentavalent impurities like arsenic, antimony, phosphorus, isn't it? And because they donate free electrons, we also call them donor impurities, isn't it? Fine. And here, to prepare P-type semiconductor out of tetravalent semiconductor, we need to add trivalent impurities, correct? Like aluminum, gallium, indium, correct? And because trivalent impurities have in the one of the surrounding bonds, they have hole, and hole has a tendency to accept electron. That's why we call these trivalent impurities as acceptor impurities also. Fine. So here we need to add pentavalent or donor impurities, and here we need to add trivalent or acceptor impurities. Fine. Then second point, its majority charge carrier is negatively charged free electron. For N-type semiconductor, you are knowing that majority charge carrier is negatively charged free electron. Fine. And here for P-type semiconductor, what is the majority charge carrier? Holes which behave as if they are positive charges. Fine. Here majority conduction of electricity takes place through free electrons in conduction band with more energy. See, last time we had cleared this point. Here in N-type semiconductor, majority of electricity is conducted by free electrons with high energy in conduction band. Remembered? Fine. Here for P-type semiconductor, majority electricity is conducted through holes, that too with low energy and in valence band. Here with high energy, here with low energy. Here through free electrons, here through holes. Here in conduction band and here in valence band. Okay, fine. And last point, here very little conduction of electricity takes place through minority charge carriers, that are holes. For N-type semiconductor, what are minority charge carriers? Holes. So very little conduction of electricity takes place through holes, and that too in valence band. Here very little conduction of electricity takes place through free electrons, and that too in conduction band. Remember, conduction band never has holes and valence band never has free electrons. Okay, I repeat, conduction band does not have holes and valence band does not have free electrons. Okay, fine. Now we go for band theory for pure semiconductor. We are talking about semiconductor. Okay, let us consider this example of silicon. For silicon, you know, atomic number is 14, so we should configure for 14 electrons, correct? Come on, electronic configuration for an atom having 14 electrons, you know from chemistry, 1s2, 2s2, 2p6, 3s2, 3p2, fine. 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 2, 14, okay? And this 3s2 and 3p2, 2 plus 2, in all 4 are valence electrons with each silicon atom. Because each silicon atom has 4 valence electrons, we call silicon as tetravalent, correct? Fine. Now tell me, as such with a 3s orbital, there are 2 energy levels possible, and with a 3p, there are in all 6 energy levels possible. So 6 plus 2, totally 8 energy levels are possible for the outermost electrons, correct? For one atom, if there are 8 energy levels possible, then for n atoms, how many energy levels are possible? 8 into n. How many? 8 into n. Out of 8 into n, you know, each silicon atom has only 4 valence electrons. So out of 8 into n, that many energy levels, only 4n number of energy levels are occupied by 4n number of valence electrons. Look, here I am showing those 4n number of energy levels which are very close to each other, and each of them is occupied by one valence electron, and because these energy levels are lying very close to each other, we can say as if they form one band which we call valence band, in which each energy level is occupied by one valence electron. So 4n number of valence electrons and 4n number of energy levels are completely occupied by valence electrons at absolute zero temperature. Okay, fine. Above this valence band, we have some region in which there are no energy levels. Come on. Here in this region, because there are no energy levels, we call this region as forbidden gap. Forbidden gap. Fine. And above forbidden gap, again we have defined energy levels, and they are remaining. Out of 8n, if you subtract 4n, then what is remaining? 4n number of energy levels are remaining. They are these energy levels, and because these energy levels are also lying very close, as if they form one band which we call conduction band. Because any electron coming in this band is responsible for conduction of electricity. That's why we call that band as conduction band. Fine. Now, this difference of energy between these two energy levels is called energy gap. If you want to define it very precisely, it is like this. The difference in energy between lowest energy level of conduction band and highest energy level of valence band is called energy gap. Is called energy gap. And for silicon, this energy gap is 1.1 electron volt. Normally for all semiconductors, this energy gap is found to be less than 3 electron volt. Less than 3 electron volt. You can see this value is also less than 3 electron volt. Correct? Now tell me, at absolute zero temperature, all the valence electrons are present in the valence band. Now because at absolute zero temperature they don't have any energy, so they cannot make any transition on their own, and unless and until some energy is supplied which is more than this, no electron can go from valence band to conduction band. So at absolute zero temperature in a pure semiconductor, there are no electrons in the conduction band is completely empty, and because there are no free mobile charges in the conduction band, no electricity can be conducted. If no electricity is conducted, you can say semiconductor will behave like an insulator, That's why remember, all semiconductors, all pure semiconductors will behave like insulators at absolute zero temperature. Got it? Fine. Now we go for metals. For metals, what is the situation I am showing you? For example, consider sodium. For sodium, what is the electronic configuration? 1s2, 2s2, 2p6, 3s1. Correct? As such, with a 3s orbital, how many energy levels are possible? 2 energy levels. Correct? With one atom, if there are 2 energy levels possible, then with n number of atoms, what is the total number of energy levels possible? 2 into n. But sodium atom has only one valence electron. So if one atom has one valence electron, then n number of atoms will have n number of valence electrons. Out of 2n energy levels, n number of energy levels are occupied by n number of valence electrons. That's why here I am showing you 2n number of energy levels, out of which n number of energy levels have been occupied by n number of valence electrons. Okay. So one valence electron occupies one energy level. Got it? And out of 2n, if n are occupied, remaining n are lying empty. But in case of metals, remember, there is no forbidden gap. There is no separation between conduction band and valence band. There is no separation. There is no gap. So you can say this energy gap for metals, this energy gap has become zero. In some of the metals, these two bands are overlapping. They are overlapping. Fine. So in metals, remember, there is no energy gap. That's why just to migrate from one energy level to another energy level, electrons will not have to make any transition, will not require any energy. They can simply roam about anywhere. Correct? Free of cost, they can just roam about everywhere, and because they can just move randomly, freely, we call them free electrons, and because of their motion of free electrons, we get conduction of electricity. Correct? That's why metals are found to be good conductors of electricity. Okay, fine. What about non-conductors or insulators? In case of non-conductors or insulators, remember, this energy gap is more than 3 electron volt. If this energy gap is very large, then what will happen for insulators or non-conductors? All the electrons are there in the valence band only. Not a single electron can make any transition. It can't go into the conduction band, and when there are no electrons in the conduction band, naturally conduction of electricity will not be possible. That's why these materials are called non-conductors or insulators of electricity, in which this energy gap is very large. It is greater than 3 electron volt. Got it? Fine. Now, let us talk about rate of recombination. Listen, at room temperature, in the pure semiconductor, might be doped semiconductor, but in any semiconductor at room temperature, what happens? Whether you are talking about intrinsic semiconductor or extrinsic semiconductor, in every semiconductor at room temperature, what happens? Some of the covalent bonds are getting broken. When one covalent bond is getting broken, it creates a pair of free electron and hole. So breaking means separating free electron from the hole. Correct? So that is a process of dissociation. Because they are getting separated. But then don't be misunderstood. If hole is created in one of the bonds, then don't think that permanently it will have hole only. No. There are more than enough chances that another electron may occupy that hole, and as soon as another electron occupies that particular hole, it no more remains a hole. So that process is called recombination. Correct? So dissociation creates electron and hole, make them separated, and recombination just prepares that bond again. Okay? So in the process of recombination, what happens? That covalent bond is getting reformed. Covalent bond is getting reformed, correct? So this process of dissociation and association of free electron and hole continuously takes place. Breaking of bond and reforming of bond continuously takes place in the semiconductor, correct? And at a given temperature, we find that whatever is the rate of dissociation, same is the rate of association, correct? Whatever is the rate of departure, whatever is the rate of dissociation, same is the rate of recombination also. Fine. Now, that rate of recombination of free electron and hole is found to be directly proportional to product of free electron number density and hole number density. I repeat, in any semiconductor, rate of recombination of free electron and hole is directly proportional to product of free electron number density and hole number density. Come on, remove this sign of proportionality, put some proportionality constant, say capital R, which is called combination coefficient. This is called recombination coefficient. Come on, recombination coefficient. What is capital R known as? Recombination coefficient. What is capital R proportionality constant known as? Recombination coefficient. Okay, fine. Now this you are talking about extrinsic semiconductor. If it is N-type semiconductor, then Ne is greater than NH. If it is P-type semiconductor, then NH greater than Ne. Okay. Now let us talk about rate of recombination for intrinsic semiconductor. Rate of recombination for intrinsic semiconductor. In case of intrinsic semiconductor, you have studied that free electron number density and hole number density are equal. Because Ne and NH values are equal, let them be shown by same symbol, let it be Ni. This is, come on, number density of intrinsic charge carriers. Number density for intrinsic charge carriers. Okay, fine. Now in place of Ne and in place of NH, I can write Ni. Just write it here. So when you write it here, Ni and Ni, so it will be R into Ni square. Here it is, R into Ni square, correct? This is rate of recombination for intrinsic semiconductor. This is the rate of recombination for extrinsic semiconductor. Now, from the laws of thermodynamics, we have come to know that whatever is the rate of recombination for intrinsic semiconductor, same is the rate of recombination for extrinsic semiconductor, which has been prepared out of that intrinsic semiconductor at a given temperature. Both the rates are equal. If both these two rates are equal, then you can compare this with this. Come on, R into Ni square should be equal to R into Ne into H. Should be equal to R into Ne into H. Come on, R into Ni square should be equal to R into Ne into NH. Now just cancel R. Cancel R from both the sides. If you cancel R, then come on. If you cancel R, then come on. Ni square will be equal to Ne into NH. Ni square will be equal to Ne into NH. Just remember, what is Ni? Number density for intrinsic charge carriers, and that is for intrinsic semiconductor. This is free electron number density, this is hole number density. If you are talking about N-type semiconductor, N-type extrinsic semiconductor, then N is greater than NH. If you are talking about P-type extrinsic semiconductor, then NH is greater than Ne, correct? Remember this formula because it will be utilized in one of the numericals also, in the MCQ also. Ni square equals to Ne into NH, correct? Fine. Now we go for studying one very important short note, because rest of the chapter is based upon this article. Please try to understand perfectly. Come on, what is it about? P-N junction. P-N junction. If one P-type semiconductor and one N-type semiconductor are joined permanently, then the whole construction is called P-N junction. What is it called? P-N junction. Here it is. Consider this as P-type semiconductor, correct? Consider this as N-type semiconductor. When you join them, the whole construction is known as, whole formation is known as P-N junction. This is the contact surface, which is called junction. Contact surface is called only junction. The whole formation is called P-N junction. For p-type semiconductor, everybody knows that majority charge carriers are holes. Fine. So I am showing you very large number of holes here. It has minority charge carrier in the form of free electron. Because they are minority, you must show them by very small number. For N-type semiconductor, majority charge carriers are free electrons and minority charge carriers are holes. Correct? Fine. Now when you join them, you know what happens immediately after that? Look. Here for N-type semiconductor, remember we had added pentavalent impurity such as arsenic. And here for p-type semiconductor we had added trivalent impurity, come on, such as aluminum. What was the speciality of this arsenic? For arsenic it is pentavalent, and so all the covalent bonds are completely filled up and plus one more fifth extra electron is left. Come on, this is extra electron, that is fifth electron. Come on, because this arsenic is pentavalent, this one I am showing as fifth extra electron. And on opposite side we have here aluminum atom, in which out of the 4 covalent bonds, in one of the bond we have hole. So this is a hole. This is a hole. Now tell me, here free electron number density is very large because of very large number, and here free electron number density is very small. So now when you join N-type semiconductor with P-type semiconductor, then simply at the time of joining, at once with a very high speed, the very large number of free electrons will simply migrate from N to P-type semiconductor, because they will just migrate from higher density to lower density. So they will migrate from N to P-type semiconductor. Now just consider this collective transformation of free electrons from N to P-type semiconductor. When you join N and P-type semiconductor, at the same time, it so happens there is a mass transfer of free electrons from N-type semiconductor to P-type semiconductor. Such a quick and mass transfer of free electrons is known as diffusion. What is it called? Diffusion. So that diffusion starts. Now tell me, if one electron diffuses from N to P-type semiconductor, what will happen? I am showing you. Here we have arsenic and here we have aluminum as impurity atoms. Now this is pentavalent, this is trivalent. Here it has one extra electron, here this has one hole. And now because electron is transferring from N to P-type semiconductor, if this electron is just migrating through this junction into P-type semiconductor, it will associate with this hole. Because electron has been transferred, this atom has lost one electron. After losing one electron, it will be transformed into positive ion. So here I am showing you positive ion, correct? And that electron will associate with this hole, and because this atom, which was earlier electrically neutral, but now it receives extra electron, then it will become negative ion. So here, after losing electrons, the arsenic atoms near the junction will be transformed into positive ions, and here aluminum atoms after receiving extra electron will get transformed into negative ions, correct? Now tell me, this part achieves positive potential, this part achieves negative potential, so you will have electric field generated between this positive to this negative part, and those electric field lines I am showing by these arrows, correct? These arrows indicate the electric field generated between these two parts, okay? Now tell me, during diffusion what happens? There is a transfer of very large number of electrons from N to P-type semiconductor. So as more and more electrons transfer from N to P-type semiconductor, then here we will have formation of more and more positive ions, and here we will have formation of more and more negative ions. As positive potential increases here it becomes more and more positive, here potential becomes more and more negative. In short, potential difference between these two parts goes on increasing. At that time, this electric field becomes gradually stronger and stronger. The strength of electric field goes on increasing. At one stage, this electric field becomes sufficiently strong such that now not a single electron can dare to enter from N to P type semiconductor. Why? Because now if any electron wants to migrate from N to P type semiconductor, then first of all it will have to cross this strong electric field, and that job is now very difficult because these electrons are at room temperature. At room temperature they have got limited kinetic energy, and with that limited kinetic energy, if any electron tries to go from here to here, first of all it will enter into this region, and as soon as it enters here, electron has a negative charge, and negative charge is always getting accelerated in a direction opposite to electric field. If electric field is toward the right hand side this way, then electron will be accelerated in just opposite direction. So as soon as any electron tries to enter in this region, immediately this strong electric field repels that electron this way, okay. So this electron will be coming back into the same N-type semiconductor. Now not a single electron is going from N to P-type semiconductor. If not a single electron is going from N to P-type semiconductor, you can say diffusion process has been stopped. Diffusion process has been stopped. Then you may have a question, how earlier electrons could go from N to P-type semiconductor? Because at that time this electric field was weak. When electric field was weak, at that time electron was successful in doing work against this electric field. It could enter from N to P-type semiconductor. But now this electrical field has become very strong. It will not allow any electron to go from N to P-type semiconductor, means the diffusion process has been stopped. When diffusion process stops, at that time we have this narrow region around this junction in which here only positive ions are there, here only negative ions are there. In short, in this region there are no free charge carriers, no free electrons, no holes, no free electrons, no holes. In short, this much part is devoid of free charge carriers. This much part is devoid of free charge carriers, means it has been depleted of, it has been separated of majority charge carriers of N and P type semiconductor. Such a part in which there are no free charge carriers, that part has been depleted, has been separated from free mobile charge carriers. That's why we call this region as depletion layer. What do we call it? Depletion layer. To be depleted of means to be separated of, to be separated of. This much part has been separated from majority charge carriers of N and P type semiconductor. That's why we call this part as depletion layer. Remember, the process of formation of depletion layer is a very fast process. Within few moments, as soon as you join N and P type semiconductor, within few moments this process is getting finished and depletion layer has been formed. Its thickness is very small. Actually this layer is very narrow. Just to have clarity in the diagram, I am just showing it wider, but actually speaking it is very narrow and its thickness is very small, 0.5 micrometer. 0.5 micrometer. You know micro means 10⁻⁻⁶. Okay, fine. Now in this depletion layer, we would like to distribute electric potential, and for that we plot one graph of electric potential versus distance from the junction. If you plot that graph, you are going to get that graph like this. What does this graph indicate? Exactly at this junction, if we take potential to be 0, then as we move towards left in this direction, then potential becomes more and more positive. As we move toward the right hand side in this region, then potential becomes more and more negative. In short, this graph gives you distribution of electric potential in depletion layer. Such a distribution of electric potential is known as depletion barrier. What is it called? Depletion barrier. Sometimes we call it potential barrier. Depletion barrier or potential barrier. And now here is maximum positive potential, here is maximum negative potential. Come on, here potential value is maximum positive, here potential value is maximum negative. So if you find out this height will give you maximum potential difference at the edges of this depletion layer, and that maximum potential difference itself is known as barrier potential. What is it called? Barrier potential, shown by symbol VO. VO means barrier potential, and it is found to be of the order of 0.1 volt. For example, for silicon, that potential barrier is, that barrier potential is 0.7 volt, and for germanium, that barrier potential is 0.3 volt. For silicon, that barrier potential is 0.7 volt. For germanium, that barrier potential is 0.3 volt. Okay. Now tell me, this PN junction, we now onwards we will call it PN junction diode. PN junction diode, because diode means any object having two electrodes, correct? Any component which has two electrodes is called diode. Here we take this P-type semiconductor as anode, we take this N-type semiconductor as cathode, and because we have two electrodes, we call it diode. So now onwards, PN junction we will call PN junction diode, and this is the circuit symbol for PN junction diode in the circuit. Whenever we want to show PN junction diode in the circuit, this is the circuit symbol. In this circuit symbol, you are supposed to show one arrow. Just fill up this part with a dark color, and then here you may write P, here you may write N. This P-type semiconductor is taken as anode, and this N-type semiconductor is taken as cathode. Fine. And now this is the circuit symbol for PN junction diode. Okay. Here, while preparing this PN junction, we can have different amounts of impurity in this P and N-type semiconductor. Practically, what do we find? When we add more amount of impurity, then we get very narrow depletion layer, very narrow. In case of more amount of impurity, depletion layer is very narrow, and in that very narrow layer, the electric field is very strong. Don't you know E equals to V upon D? If D is less, then electric field will be very strong, correct? And then if you keep amount of impurity in both the semiconductors while preparing PN junction, say small. If amount of impurity is small, then we get depletion layer quite wide. So width of the depletion layer is more, and when width is more, then electric field will be weak. Okay. So what I mean to say, by just changing the amount of impurity, we can have different types of PN junctions in which there are different types of I versus V characteristics. The graph of current versus voltage is obtained different if you change the amount of impurity while preparing PN junction, correct? And depending upon that, we will have new semiconductor devices about which we are going to study in this chapter. Okay, fine. Come on, my dears, let us see now next article. Look at the title. Forward bias, static characteristics of PN junction diode. First of all, tell me, what do you mean by static characteristics? If you plot a graph of current versus voltage for PN junction diode without connecting any resistance with it, then it is called static characteristics. Okay, fine. Now, when you want to connect any battery across PN junction, we are actually biasing that PN junction. Biasing any PN junction means connecting a battery across PN junction diode. Now, battery you can connect in two different manners with a PN junction diode. If you desire, you can connect P with positive, N with negative. P with positive, N with negative. Such a connection is called forward bias connection. What is it called? Forward bias connection. P with positive, N with negative. Look here. P with positive, N with negative. Correct? It is called forward bias. And if you connect in a reverse way, P with negative, N with positive. P with negative, N with positive, then it is called reverse bias. Look here, reverse bias, correct? Let us see both these conditions one by one. First of all, we would like to discuss about forward bias condition. Fine. In order to plot forward bias static characteristics of a PN junction diode, we are supposed to connect PN junction diode in this circuit as shown in the diagram. Look, we have one battery, correct? Its negative terminal through rheostat variable terminal is connected ultimately with a N-type semiconductor. So this is negative. So here I am writing minus sign. Okay. So potential applied on this N-type semiconductor is negative, and this positive terminal is connected here with P-type semiconductor. So here potential applied is positive. N with negative, P with positive, it is called forward bias connection. Correct? Fine. Now tell me, what is the voltage across PN junction diode? Just to measure it, we connect some voltmeter in parallel. And what is the current passing through PN junction diode? To measure that current, we connect some milliammeter in the circuit in series. You know, current meters are always to be connected in series, whereas voltage meters are always to be connected in parallel. Fine. Now tell me, because this is N-type semiconductor, its majority charge carriers are negatively charged free electrons. And because this is P-type semiconductor, its majority charge carriers are holes, which behave as if they are positive charges. Fine. And at the central part, you know, we have depletion layer. Fine. Here in N-type semiconductor, this region near the junction is full of positive ions, and here this part of P-type semiconductor near the junction is full of negative ions, and there is some electric field between these positive to negative ions. So in this direction we have electric field inside this depletion layer, which are shown by symbol EI, which is from positive to negative towards right hand side in this direction. Okay, fine. When we do not put this key, when the battery is not connected, at that time the depletion barrier is this. Depletion barrier is this. Fine. In which barrier potential is this much, that is height of depletion barrier, and this much is the width of depletion layer. This much is the width of depletion layer. Initially, this is the width and this is the height of depletion barrier initially, when you have not connected any battery. Fine. Now when we put this key, battery is connected. Okay. At that time this end becomes negative, this end becomes positive. Tell me now, because this end is positive, this end is negative, you are actually applying some external electric field from positive to negative. So this is the applied electric field from positive to negative. This is the applied electric field. Correct? This is the electric field inside the depletion layer EI, that is towards the right hand side at present, and this is applied electric field which is towards left side. Now tell me, these two electric fields are in opposite direction. So whenever vectors are in opposite directions, you can subtract. Okay, then subtract smaller electric field from bigger one. This is bigger, this is smaller. Then resultant electric field will be towards left side this way. And you know, free electrons are always getting accelerated. Free electrons are always getting accelerated in a direction opposite to electric field. If resultant electric field is towards left side, then these free electrons will be accelerated this way. Correct? They will now receive energy to migrate through this electric field in the depletion layer. Correct? Now, because of this resultant electric field towards left side, these electrons now can just transfer themselves from N to P type semiconductor. They can cross this electric field and they can come here. When they come here, they will associate with these holes, and then after jumping from one to second, second to third, third to fourth, likewise they will be just jumping from one to another hole in the form of bound electrons, and then flow of electrons will start this way. If this is the direction of flow of electrons, come on, in just opposite direction you will get electric current. If direction of flow of electrons is this, then direction of flow of electric current is this. Correct? And that current which is flowing in forward bias condition is known as forward current, shown by symbol IF. So IF means forward current and VF means forward voltage. Okay, fine. Now tell me, when electrons are moving this way, the positive ions, if they receive extra electron, will get transformed into neutral arsenic atoms. And similarly, if the electrons which are here, if they migrate, if they move this way, correct, then this excess electron is removed from those aluminum atoms which were negative ions. If excess electron is removed, then they will be transformed into neutral aluminum atoms. So I mean to say, in this process, here number of positive ions will decrease, here number of negative ions will decrease, that is depletion layer will become narrow, and as the depletion layer becomes narrow, earlier it was having this much width, now it is having this much width, it has become narrow, and at the same time its height also decreases. So barrier potential decreases, and here width of depletion layer also decreases. Width of depletion layer and height of depletion barrier, both of them decrease in case of forward bias condition, correct? Same thing I am showing you here. This is the initial condition, this is the initial graph, and this is the final graph, okay, fine. Now tell me, practically what we can do here, we can slide this terminal towards left this way, and as you do that, the potential difference applied across PN junction diode will go on increasing, that is forward voltage will increase, and as forward voltage increases, every time you can measure this forward current practically, and then after you can plot a graph of IF versus VF. That graph is found to be like this, correct? Such a graph itself is known as forward bias characteristics, forward bias static characteristics of a PN junction diode. This graph itself is called forward bias static characteristics of a PN junction diode. Fine. Now here in this graph, if you observe minutely, then you will come to know from particular forward voltage, the forward current starts increasing exponentially. That particular forward voltage from which, beyond which the forward current starts increasing exponentially itself is known as threshold voltage, shown by symbol VTH, that is threshold voltage. It is also called cut-in voltage. What is it called? Cut-in voltage. Fine. Now if you want to find out resistance of forward bias, resistance of PN junction diode in forward bias condition, we call it dynamic resistance, because if you find out that resistance in different parts of this curve, it is found to be different. That's why we call it dynamic resistance of PN junction diode in forward bias condition. And for this linear portion of the graph, if you want to find out, you can just find out this delta V value and delta I value. Once you get delta V and delta I from this triangle, then you can just take ratio like this, delta V upon delta I, which will give you dynamic resistance of PN junction diode in the forward bias condition, okay. Now such a resistance is found to be very small, it is of the order of ohm, okay. So this is all about forward bias static characteristics, and now we go for reverse bias static characteristics. See the difference between these two circuit diagrams. The only difference is here is the change of polarity of this battery. Come on, change of this polarity of this meters, voltage meter and current meter. Here minus plus, here you can notice it is plus minus. Here it is minus plus this way, and here it is plus minus, okay. Here minus plus, come on, here plus minus, correct. All the three polarities you simply make them reversed, okay, fine. Now here N with positive and P with negative. Come on, N with positive, P with negative, then it is called reverse bias condition, fine. Now tell me here what will happen. Before you put this key, this is the original graph, original distribution of electric potential in the depletion layer, which we call depletion barrier. So depletion barrier is this initially, correct? But later on what happens, when we put the key, then after look, this positive terminal is connected here. So this potential is positive, similarly this potential is negative. Now tell me, the electric field inside this depletion layer is from positive to negative and this way towards the right hand side. That is what I am showing here, EI, inside electric field inside the depletion layer. But now this end is positive, this end is negative. So you are applying some external electric field from positive to negative, this way, correct? That is applied electric field. Here both these fields were in opposite directions, and here both these fields are in the same direction. So whenever vectors are in the same direction, you should make their addition. So resultant electric field is in this direction. If resultant electric field is in this direction, then tell me, electrons will be accelerated in a direction opposite to electric field. So free electrons from here will be accelerated this way, in a direction opposite to this electric field. Correct? Fine. Now those electrons will move this way. If electrons are flowing this way, current you should think in just opposite direction, this way. And this is nothing but reverse current. I am showing by symbol IR, reverse current. IF was forward current, IR is reverse current. Wait. Now these electrons will come here. Correct? Now as the arsenic atoms situated here, they have extra fifth electron, and if that fifth electron is moving this way, they will be transformed into positive ions. So I mean to say here number of positive ions will increase, and those electrons will come here, and from one to another hole, second to third hole, they will be simply jumping in the form of bound electrons. Ultimately they will arrive here, and when they will jump into one of the holes around surrounding to aluminum atom, it will make that aluminum neutral atom converted into negative ion. So here number of negative ions will go on increasing. So in this reverse bias condition, it so happens here number of positive ions goes on increasing, and here number of negative ions goes on increasing. In short, the width of depletion layer goes on increasing. As this width is increasing, this height also increases. Here in case of forward bias, height of depletion barrier and width of depletion layer both were decreasing, and here both of them are increasing. Okay, fine. Now tell me, here whatever is reverse current is flowing, that reverse current causes increase of width of depletion layer. Look here this way. Now tell me, as this width goes on increasing, this height is also increasing. Ultimately barrier potential will go on increasing. At one stage, this barrier potential becomes equal to terminal voltage of external battery. Fine. Now then after what happens? How then after current still continues? I am showing you. In this very wide depletion layer, there are plenty of covalent bonds, and at room temperature some covalent bonds are getting broken, and because of breaking of covalent bonds, certain on average constant number of covalent bonds are broken because temperature of room is constant, and then it will release constant number of electron and hole pairs. Okay, if one bond is getting broken, it will release one pair of free electron and hole. Fine. So here because of breaking of covalent bonds, there is a constant release of pairs of free electron and hole. As soon as electron is freed, it will be accelerated this way in a direction opposite to this electric field. Correct? And because of motion of electron that way in this direction, you will have constitution of current which is called reverse current. If electrons are flowing this way, reverse current you can think in the opposite direction. I am showing by symbol IR. But because room temperature is constant, on average constant number of bonds are getting broken and releasing constant number of free electrons. If constant number of free electrons take part in the flow of current, naturally the current will be constant. That's why reverse current is constant. Look here, reverse current is constant. And not only that, at room temperature very few covalent bonds are broken, releasing very few number of electrons, and if very few number of electrons take part in the conduction of current, naturally that current will be very small. It is found to be of the order of microampere, micro 10 raised to minus 6 ampere. So that current is not only constant, but it is almost zero. That very small constant current is known as reverse saturation current. Reverse saturation current. Fine. Now tell me, you slide this terminal towards left. As you go on sliding towards left, what will happen? The reverse voltage applied will go on increasing. Now tell me, this end will become more and more positive, this end will become more and more negative. Look, this end becomes more and more positive, and this end becomes more and more negative. Then at one stage it will so happen that this will become tremendously positive, this will become tremendously negative. So in this direction we will have very strong electric field, and that very strong electric field inside this PN junction diode will cause breaking of majority of covalent bonds. If it causes breaking of majority of covalent bonds, then it will release very large number of free electrons, and if very large number of electrons are freed, and if all of them take part in the conduction of electricity, naturally current will increase very fast. I mean suddenly, very briskly current will start increasing now. You can see sudden rise in the current. You can see sudden rise in the current. Earlier it was very small and constant. Now there is a sudden rise in the current because of breaking of majority of covalent bonds. That minimum reverse voltage at which breaking of majority of covalent bonds occurs, that very minimum reverse voltage is known as breakdown voltage. It is called reverse breakdown voltage. Reverse breakdown voltage. Reverse breakdown voltage shown by symbol VR. We call it reverse breakdown voltage. Fine. And then after we get sudden rise in the current. Okay. This whole graph is called reverse bias static characteristics of a PN junction diode. Reverse bias static characteristics of a PN junction diode. Now here in this linear part of this graph, if you want to find out resistance, we call it dynamic resistance of PN junction diode in a reverse bias condition. And here also you can find out delta V upon delta I. You can take this ratio this way, and then that resistance is found to be of the order of mega ohm. So it is very large resistance, very large resistance. Okay. Now tell me, this forward voltage is taken on positive x-axis. Because reverse voltage polarity is opposite to that, we take it on negative x-axis. Forward current is taken on positive y-axis. Because flow of reverse current is just opposite to flow of forward current, we take it on negative y-axis. In short, this graph is to be plotted in first quadrant and this graph is to be plotted in third quadrant. Got it? Fine. Now we go for very important article. See the title. What is called rectification and rectifier. Look, Torrent Power Limited, that company delivers electrical power at our residence, correct? But that power is delivered in the form of AC, correct? There are some reasons for that. Delivery of electrical power in form of AC is rather easy, cheap in cost, and it is less dangerous, correct? But then to run some of the household appliances like radio, TV, the cell phone charger, we require power in the form of DC. Then what to do? Whatever power we are getting in the form of AC, we should convert it into DC. So we require some device which can do this job of conversion of AC into DC. That very device itself is known as rectifier, and this process of converting AC into DC is known as rectification. Process of conversion of AC into DC is called rectification, and the device made for that is called rectifier. Okay. There are two types of rectifiers. One is called half wave rectifier, another is called full wave rectifier. Let us see about them one by one. Okay. First of all, we take half wave rectifier. Here it is. Use of PN junction diode as half wave rectifier. This is the necessary circuit diagram for that. You can see AC source. This is the circuit symbol for AC source, which is connected across primary coil of a transformer. And here is a secondary coil of a transformer. Its two terminals I have shown by symbols S1 and S2, out of which S1 is connected across anode of PN junction diode, that is with P-type semiconductor, and second terminal S2 is connected to cathode of PN junction diode, that is with N-type semiconductor, through some proper resistance which we call load resistance. Correct? Now any voltage obtained here across this load resistance, it is called output voltage. We will show it by symbol VO, output voltage. Fine. Now tell me, the voltage applied to this primary, it is alternating, and you can show it this way, correct? This is called negative going half cycle, this is called positive going half cycle. Now according to Lenz's law, the EMF developed across this secondary coil will just try to oppose the very cause producing it, and that's why the polarity of this signal, you can see it is just opposite to this, Here minus plus, then here I am writing plus minus, correct? This is called positive going half cycle between 0 to t by 2. This is called negative going half cycle between t by 2 to t, correct? Let us start now discussing working of this device in these two time intervals from 0 to t by 2 and then after from t by 2 to t. Fine. First of all, take this interval 0 to t by 2. In the time interval from 0 to t by 2, tell me the potential at S1 with respect to S2. Potential at S1 is from 0 to t by 2, it is positive. So potential at S1 is positive. Potential at S1 is positive. So here positive potential is applied. Come on. With respect to S2, if S1 is at positive potential, then with respect to S1, S2 will be at negative potential and that negative potential will be here. So I mean to say P with positive and with negative. P with positive and with negative. P with positive and with negative. Arey Baba, it is nothing but forward bias condition. And in case of forward bias condition, we have current passing through this PN junction diode. In case of forward bias condition, we get current through PN junction diode. Look here this way, correct? We get this forward current in this direction. In this direction means what? Inside this PN junction diode, it is from P to N. From P to N. From P to N this way, correct? Fine. When you get current in this direction, that is in the direction of arrow, we will get some current and that current will pass through this load resistance in this direction, this way. So this is how current flows as long as the potential at S1 remains positive. Current is flowing this way and through this load resistance, current is flowing this way from A to B. Fine. So that current is flowing from A to B. Now tell me, where is the conventional direction of current? It is always from positive potential to negative potential. So if current is flowing from A to B, A must be at positive potential and B must be at negative potential, correct? And suppose here in the output voltage VO, suppose I am showing potential at A with respect to B, then potential at A with respect to B is positive. Because potential at A with respect to B is positive, then I am showing here positive going half cycle. Positive going half cycle from 0 to t by 2. Got it? Fine. Now let us consider next half cycle, that is from t by 2 to t. From t by 2 to t. Tell me, from t by 2 to t, come on, potential at S1 with respect to S2 is negative. So here potential is negative. Here potential is negative. Come on. With respect to S2, if S1 is at negative potential, then with respect to S1, S2 will be at positive potential. So here you can see now, potential at P is negative, potential at N is positive. P with negative, N with positive. P with negative, N with positive. Arey Baba, this is reverse bias condition. And in case of reverse bias condition, almost there is no current. For ideal PN junction diode, when you operate it in reverse bias condition for voltage less than reverse breakdown voltage, then the reverse saturation current is there, which is nearly zero. So for ideal PN junction diode, we will say there is no reverse bias current. Okay? When there is no current here, no current through this resistance, then we will not have any voltage across this resistance, because voltage across any resistance means current into resistance. When current is not there, there is no voltage. That's why I am showing you some gap here between t by 2 to t. There is no output voltage. That's why I am showing you gap. Okay, fine. Now tell me, what does it mean? As long as there is positive going half cycle in this secondary voltage, come on, there is output voltage. But when there is negative going half cycle in this secondary voltage, there is no output voltage. Once again in the secondary voltage, when there is positive going half cycle, once again we will get output voltage. Once again when there is negative going half cycle in this secondary voltage, we will not get any output voltage. So that is why I want to say, if there is no current through RL, no problem. But whenever there is a current through RL, it is flowing in one direction, always from A to B. If any current is there which is flowing always in one direction, it is called unidirectional current. In short, we call it direct current. In short, we write it DC. So this current passing through RL is DC. Correct? Fine. What you had actually, you had AC. And now what have you got? DC. See, if you connect this source directly with load resistance RL here, if you connect it here, then current passing through RL will just go on changing alternatively, direction wise, correct? But here, through PN junction diode, when you connect this way in this circuit diagram, then current passing through RL is always flowing. Whenever it is flowing in one direction only. Such a current is called direct current DC. What you had AC, what have you obtained is DC. Process of conversion of AC into DC is called rectification, and this device made for that is called rectifier. That's why I'll call it rectifier. Fine. But because we get output voltage only for half of full cycle of secondary voltage, we call it half wave rectifier. Because we get output voltage only for half of full cycle of secondary voltage. That's why we call it half wave rectifier. Correct? Fine. Now we go for use of PN junction diode as a full wave rectifier. As a full wave rectifier. Tell me what is the difference between this circuit and this circuit? There are two differences. Come on. We are using here special type of transformer in which extra connection is taken from center of this secondary coil. To take extra connection, in English language we call it to do tapping. To do tapping. To do tapping means to take extra connection. Because extra connection is taken from center terminal, we call it center tapped transformer. Come on, we call it center tapped transformer. Center tapped transformer. Fine. So here we are supposed to use, come on, center tapped transformer. Fine. And then what is one more difference? Instead of one PN junction diode, we have employed, come on, two PN junction diodes, come on, D1 and D2. How is the connection I am showing you? First of all, AC source is connected as usual with the two ends of primary coil of a transformer. Then across the two ends of secondary coil, with one end we just connect a anode of one PN junction diode, with another end we connect anode of another PN junction diode. Fine. And then after cathodes of those two PN junction diodes are interconnected at this point. And this common point of interconnection is connected to this center terminal. This symbol indicates that these two wires are overlapping, but the currents are not getting mixed up. Currents are not getting mixed up. Okay, fine. Now tell me, let us start working of this device. Come on. Here if you apply AC voltage, then you may show it this way, negative and positive. But according to Lenz's law, the EMF induced across the two ends of secondary coil will try to oppose this, and in short, its polarity will be opposite to this. Come on, here plus minus, correct? This is the potential at S1 with respect to S2, then potential at S2 with respect to S1 will be just opposite to this. So here plus minus, then here you should write minus plus. Fine. Come on, start the working in two different time intervals. First of all, we take 0 to T by 2. From 0 to T by 2, potential at S1 is positive, but potential at S2 is negative. So potential at S1 is positive, but potential at S2 is negative. Now tell me, P with positive, P with positive. So this diode is under forward bias condition, and here P with negative. So this diode is in reverse bias condition. When this is in reverse bias condition, it will not allow any current to pass through it. Fine. But because this is forward bias, it will allow current to pass through it in the direction of arrow this way. And that current will come up to this point, but then after it will not flow here because this is already in reverse bias condition. So that current will start flowing this way. Correct? And then that current is flowing this way. And when it is flowing through load resistance, it is flowing from A to B. So that current is flowing from A to B. Tell me, where do you show the direction of current? Always from positive to negative. So if current is flowing from A to B, A must be at positive potential and B must be at negative potential. Correct? And here in the output voltage, what do we show? Potential at A with respect to B, which is right now positive. Because potential at A with respect to B is positive, we can show here positive going half cycle from 0 to T by 2. Fine. Now tell me, what about next half cycle? Next half cycle is from T by 2 to T. From T by 2 to T, potential at S1 is negative. Potential at S1 is negative. Now tell me, potential at S1 is negative, but potential at S2 in this time interval is positive. So here P with positive, so now this diode is forward bias, and here P with negative, so this diode is reverse bias. This will not allow any current to pass through it, but because this is forward bias, it will allow current to pass through it in the direction of arrow, this way, look. And then after this, current will come up to this junction. It will not flow here because this is already in reverse bias condition. So that current will continue to flow this way, look here, this way, correct? This is how current is flowing, come on, fine. And when that current is flowing through RL, it is again flowing from A to B only in the same direction, from A to B. But current is always from positive to negative. So potential at A must be positive, potential at B must be negative. And what do we show here in the graph in the output voltage? Potential at A with respect to B. Potential at A with respect to B is positive. Because it is positive, we must show, come on, positive going half cycle in the time interval from T by 2 to T. What does it mean? For the secondary voltage, whether it is positive going half cycle or negative going half cycle, irrespective of that, every time we are going to get positive going half cycles in the output. And tell me, every time current through RL is flowing only in one direction, any current which is flowing always in one direction is called unidirectional current. We call it direct current, shortly written as DC. So the current passing through load resistance is DC. Fine. Tell me what you had actually. You had actually AC. If you connect this source here across RL directly, then you will have current passing through RL changing the direction alternatively, correct? So it will flow in both the directions, clockwise and anti-clockwise also. But here, through these two PN junction diodes, when we connect AC source this way, then current through RL is found to be unidirectional, that is direct current, that is DC. Process of conversion of AC into DC is called rectification, and the device made for that is called rectifier. So I can call this device as rectifier, correct? But because we get output voltage for full cycle of secondary voltage, we call it, come on, full wave rectifier. What do we call it? Full wave rectifier. But have you noticed one thing? Whether it is half wave rectifier or it is full wave rectifier, one thing is certain, that so far magnitude of voltage is concerned, it is increasing, decreasing, increasing, decreasing. Look here, increasing, decreasing. And such voltage is called pulsating voltage. What is it called? Pulsating voltage. Then we would like to minimize these pulsations. If you want to make that voltage rather smooth, then you are supposed to use one specific type of circuit which is called filter circuit. What is it called? Filter circuit. The details of which you will study in your higher standards, but right now I am giving you a very simple example of a filter circuit. Look, here is AC voltage which is applied to rectifier. In the output of rectifier, we have pulsating DC, out of which we would like to remove the pulsation. We would like to make that voltage rather smooth and constant. And for that, what we do, we just connect one capacitor here having very high capacitance, and one load resistance is connected this way. Fine. Now see what happens. You know the formula of magnitude of capacitive reactance. Magnitude of capacitive reactance is Xc equals to 1 upon omega C. Now if you keep the capacitance value very large, when capacitance is very large, naturally Xc will be very small. So very small resistance will be offered to the flow of AC through this capacitor during charging and discharging. And because very small resistance is offered, then AC is getting bypass. AC is getting bypass through this capacitor. It doesn't flow ahead. It doesn't flow ahead. And the part of the current which is flowing ahead, it is having majority of the components in the form of DC only, because AC is bypass and then only DC components are proceeding further. And so across RL we will get almost constant DC voltage. Okay. So this is how, using filter circuit, we can minimize the pulsation, we can make the output voltage of rectifier rather smooth, correct? This is the use of filter circuit. Here we have employed capacitor. If you desire, you may employ inductor also, about which you will study in your higher standards. Okay. Thank you.